informatics folks there now. So I'm going to talk today about connecting the dots, collaborative analytics at scale. And I think, in the context of the DREAM challenges, you all are presented or are helping design challenges where you have, training data set that we want to sort of have competitions around to help develop, the best possible machine learning or other types of algorithms to understand, key and significant biological questions. But what many of you may not realize is, how much preparation goes on before those data sets get delivered to you. And so my talk today is hopefully going to inspire you to wonder where your data has been, how did the dots get connected, and if you are in the business of connecting the dots yourselves, that you understand a little bit more about some of the methodologies that I think are really quite as much innovative as the machine learning and other algorithmic work that we do at the other end. So hopefully it will inspire new kinds of DREAM challenges and new approaches to improving our data quality and data utility in the context of our algorithmic work. So interoperability is in the eye of the beholder. And I just wanted to talk a little bit about this because I do think it really, all four of these categories really influence what we're able to do in the DREAM community in particular, but in the informatics community in general. And the first is legal and licensing. I could give a whole keynote on that and the escapades that I've had with my various legal teams to get access to and be able to redistribute data. Just because it's available doesn't mean it's legally redistributable. And so, really thinking carefully about when we do share data or when we reuse and redistribute data, what are the licensing terms of those data? The second barrier to interoperability is regulatory barrier and really being able to match the access control with the provenance of the regulatory permission. Now, that gets really complicated when we think about the transitive nature of how data gets manipulated and handed off from one person to the next in a bucket brigade. So we need to understand how those regulatory and access permissions align with the consent, especially for patient-generated data. Of course, there are system interoperability. Platforms and tools often cannot talk to each other in order to move data and analyses around. In the world of containerization, we've made great improvements in this, but we still have gaps, especially when we have very large data sets or data sets that cannot be moved for one reason or another, and I'm going to talk about one of those today. And then finally, the main theme of my talk is data and how it's often unencoded or coded in different models, terminologies, limiting search and integrating analytics. So we want to go from practice-based evidence to evidence-based practice in medicine. And much of my work is focused on the sort of translation of everything from basic research to public health data to the actual arena of clinical practice. So we have data that lives in clinical warehouses that comes from patient encounters. We have registries and marks that those data end up in. We infer new knowledge, new medical knowledge from those contexts. And then we have, this process that's probably the most amorphous part of this whole cycle is how do you turn that knowledge into clinical guidelines and care? And that we, in the clinical informatics community, we call that the last mile implementation of science. And that's how it gets into clinical decision support systems and tools that are actually used by clinicians on a day-to-day basis. But in order to have practice-based evidence leading to evidence-based practice, we need to have comparable and consistent information and harmonized data at every step of this path. And so that's really what the impacts of being able to have comparable and consistent data are just tremendous. And in this country, and we're going to get to this later, we don't have centralized healthcare, and therefore we don't have centralized healthcare data. So how do we analyze the data in a comparable and consistent manner when standards and the tools that we have and all the things on the prior side really are not aligned for us to be able to do large-scale machine learning and analytics on things that's fundamentally not comparable and consistent? So I wanted to talk a little bit about distributed data versus aggregated data versus truly integrated data. If we think about sort of distributed data, we have lots and lots and lots of distributed data systems, and I think NIH might fund a new one every week, where species-specific or data type-specific lines of inquiry, are collected into a database. But those databases are not necessarily designed for interoperability, even though they may use their own internal standards, working standards. Aggregated data is basically large-scale indexing, and it's really useful for generalized search and retrieval. And we all use Google every day. It has many very interesting algorithms for helping search optimization. But fundamentally, it's a large-scale indexing effort. It's not really largely, with the exception of Wikidata and the ways in which those kinds of things get promoted. Not really, thinking about knowledge transfer or knowledge management per se. But when we have truly integrated data, we get this picture. And this careful alignment of distributed data and shared conceptual frameworks and using consistent identifiers to really integrate data can really give us this cross-domain insight by both machines and humans. So I want to talk a little bit about addressing the mapping problem, which is both at the schema and the value level. So if you look at my little cartoon on the left of two different data schemas, they have different tables. Within one of those tables, the two green ones, we might have values that are in common within those tables, right? And so fundamentally, when we want to integrate data, we have to think about it both on the terminological value set level as well as on the schema alignment level. So for example, in one schema, we might not have a direct link between a sample and a diagnosis, whereas in another, we would. And so in order to take the one that doesn't, we have to, quote, remodel the sample case table, the diagnosis case, and then somehow create a derived table that would, be able to give us the sample to diagnosis. And you're all very familiar with these kinds of approaches of sort of extracting and joining various bits of various tables in order to remodel these schemas. But doing it in a reproducible way at scale is really challenging. And that's one of the things that we've been really trying to tackle. I also wanted to give an example of the terminological alignment. And it's something, again, that I think everyone faces. We have different systems that provide us different data with different values. So at the top, this is a race example where we have 4 values: not reported, white, American Indian, or Alaskan Native, or Black or African American. Whereas another source, and this is a real example, has not allowed to collect unknown white, Native, Hawaiian, or other Pacific Islander, American Indian, Alaskan Native, Asian, other, or Black or African American. Now, you can see the ones that are in common, but what do you do with the ones that aren't? So if I let's say I'm trying to collapse the ones on the bottom with the target just the top. Well, not allowed to collect is not the same as not reported. Not exactly. And same thing with others. So if we're going to lump other and unknown and not allowed to collect into not reported, we want to know the provenance of that so that when we evaluate the not reported, we really understand the meaning of what that means. So if other, for example, is included and not reported, we're basically excluding a potentially significant large number of other sorts of races. So online. Okay. Okay, the problem is I can't see my slides. So, well, they're too small. So how do I get them to just be, that's probably too late for that. I'll do my best. Okay. Displays. Okay, thanks. Sorry about that. So basically we want to know that, individual, patients or participants have recorded an other race. If that's going to not report it, that's inequitable. That's not, letting us ask some of the kinds of questions that we might want to ask about race in the data sets. We just need to know the provenance of that if we're going to make those decisions. And that provenance is very rarely ever tracked. Okay, so let's talk some more about entity field value mapping. So here we have two things, Friedreich's ataxia and OMOP 441554. And so we want to understand what's the relationship between these two things. There's a label over there on the left, and there's an identifier on the right in the form of a query. So the entities are the symbols, such as codes in a terminology, classes in ontology, enumerations in a data model, or simply strings in a text field that refer to a real-world thing, right? So Friedreich's ataxia is a real-world thing, and it's associated with this identifier. Okay, but what do we mean by that association? Is it just an association, like you don't qualify that association?
Is it an instruction for replacement? Every time I see OMOP 441554, replace it with that string. Is it a rule or function? Is it telling me that that it's a classification for a diagnosis in a particular clinical context? So there's all kinds of different meanings that we can have about the relationship between a term, identifier, and between terms. So this kind of mapping goes on all over the place. So we have source terminology mapping from one to another. We have, something encoded in the National Cancer Institute's thesaurus mapped to, ICD-10. And so there's lots and lots of examples of that. And again, those associations are largely unqualified, which doesn't mean to have that mapping. Then we have organizations like Odyssey, the UMLS, or the NCIT itself, which I call mappers, which basically are large collections of mappings that say, oh, I've got this FilmEd code, this ICD code, this NCIT code, and they're all mapped together. But again, so they're collections of mappings, and they perform these mapping functions, but we don't necessarily know what the relationships are between those terms. Then we have the problem of coded data and unencoded data. So in clinical systems, locally, there's often a lot of local terms that don't have codes, and those have to be mapped to things with codes in order to make them shareable and computable. Or they have local codes, and those local codes must be mapped to a function. And then finally, we have things called code sets, which are essentially representations of a particular phenotype or a particular diagnosis. So for example, if I want to query an electronic health record system for all the patients that have diabetes type 2, it's not going to be just one code. It's going to be a collection of codes. It might be codes that involve multiple types of diabetes. It might be codes that involve laboratory values. And so that collection of things we call a code set. And those two are essentially a kind of a mapping that represents an entity diabetes type 2. So furthermore, there's other kinds of mappings which have to do with sort of definitions of the things that we're talking about. So here, and I'm going to use for my first set of examples, kind of disease entities as one of the problem spaces. So different organizations annotate different relationships to disease entities at different levels of granularity. And so this is a different kind of mapping. And if you think about, we have like ClinVar, which maps disease entities to a variant. The disease has an identifier associated with it as a variant. OMIM captures information about diseases to genes. Our group, who leads the human phenotype ontology, captures diseases to phenotypes. We have a comparative toxicogenomics database and ClinGen that capture information about treatments and the relationship between exposures and diseases. And different communities are using these identifier systems in different ways to capture different mappings or associations across the spectrum. And fundamentally, if we want to understand disease, say diabetes type 2, we want to be able to collect all that information and have it all work together from all the different sources that are capturing that information. So how do we harmonize this world? There are many different disease terminologies. There are complex ones: cancer, infectious diseases, rare diseases, Mendelian diseases. There are hundreds and hundreds of disease terminologies. And each one of those disease terminologies is used in all the ways that I showed on the prior slide. So if we want to aggregate the knowledge about these diseases, we need to figure out how to reconcile the diseases themselves. And these diseases are often mapped to each other, as I mentioned, and they have their mappings made available, and these mappings are useful to crosswalk across systems. And so how many of you in the room have ever used identifier mapping in any of your work? Really only one person? Okay, well, maybe there's an identifier mapping challenge in our future. The problems are that these mappings are often mutually inconsistent. One source will map to another source, but then the second source will not map back to the first source, will map to something different in the first source. So the mappings are also not really equivalent. Sometimes a mapping will be from a parent to a child in another terminology or to a group of terms. They're not one-to-one equivalents. And just fundamentally, there's n squared minus n sets of mappings if you collect all the mappings. And so it's just a lot of mapping. Really gives you nightmares. There's an example. So here I'm looking at peroxisome biogenesis disorder and its relationship to Zellweger syndrome. And you can see over there on the left from Orphanet that peroxisome disorder is a child of dysbiogenesis disorder as a child with autosomal disease and has Zellweger syndrome as a child. Whereas Zellweger syndrome in the middle from the NCIT is a child with leukodystrophy, which has a different relationship to a variety of other disorders that aren't shown on the left. And then we have the disease ontology where Zellweger syndrome is a child with autosomal disease directly. And so there are different labels for many of these related terms, different parents, different children's, different synonyms, and different text definitions. So if I'm a clinician trying to diagnose a patient with Zellweger syndrome, which definition do I use? And it's very hard to reconcile these definitions across sources. So we worked with a large community to take all of these different knowledge sources and try to reconcile them within an algorithm called the KBOOM, or Bayesian Owl Ontology Merging Algorithm, which is a logical and probabilistic inference machine that tries to find equivalencies across different terminologies based on different characteristics, and then generates a probability score of their equivalency. And then following that, the curator will go through and really try to understand what, for those low probability equivalence tweaks, which ones can be reconciled by upstream errors in source ontologies and so forth. By doing this, for example, and then that information all goes back to both the source ontologies and to a fully curated ontology called Mondo, which contains the fully provenance mappings finally for the first time for how we've actually created those mappings. And we found some really interesting things and have really improved a lot of the source terminologies that are used for different things. So for example, we found a whole branch of MESH, the medical subject headings terminology that's used to index Medline, where a whole disease branch was duplicated with alphanumeric and Roman numerals. So we had diabetes type 2 with the number 2 and diabetes type 2 with the Roman numeral 2. And nobody had realized that. And so when you're querying the literature for diabetes type 2, you're only going to get some proportion of the records because the other half have been indexed with the other term, right? And so that the reconciliation of all of that is improving the upstream resources. So we then asked, so reconciling the bits, so coming back to this problem of like, when we're a clinician and we're trying to diagnose a patient, we need to really know what, for a rare disease, what are the candidate diagnoses that one might use, to consider for that particular patient sitting in front of you. Well, which sources you have access to really matters. So here, for example, we took 5 sources of rare disease knowledge: the NCIT, the disease ontology, NIH's GUARD platform, Orphanet, and the online Mendelian inheritance of man. And we reconciled all the rare diseases in all of these sources and then some. And we found that not only did the 5 sources that we looked at comprise approximately 10,500 different unique rare disease concepts, which is approximately 3,000 more than was originally identified in the Orphan Drug Act of 1983, and is still coded to this day, even though we've learned lots and lots of new diseases since 1983, of course, that we actually counted them for the first time since 1983. We also, but more importantly, we found that many diseases are only found in one source. So if you're in Europe and you're using only Orphanet, you're missing out on a whole bunch of other disease knowledge that's represented in these other sources. That's not health equity across the world. Only 333 concepts were in all 5 of these sources. So it really kind of speaks to the power of uniting the bits of their disease knowledge, provide now access to everyone's tools and diagnostic settings, all of the knowledge from all of these sources. Okay, a little bit more about bits and rare disease diagnostics, which was my day job before COVID happened. More about the COVID project. So why model organisms matter to patients? Plus, I especially love showing this slide. So other species aren't just relevant. Each one has unique phenotypes and bits of data that are associated with those phenotypes. We really want to understand the phylogenetic breadth of life and the relationship between genotypes and phenotypes across species, and use that information to help us with comparative medicine. And I won't go through all of the examples here, but for example, aged cats are natural models of Alzheimer's disease. Armadillos are the only host for the leprosy mycobacterium besides humans. And silkworms are a model for uric acid metabolism. So there's lots and lots of species out there, model systems, veterinary species, and evolutionary biology species that can really help us understand this relationship between genotype, phenotype, and the environment that we want to try to make computable. So And this is a testament to that fact. So over on the left, we took the 19,201 human coding genes that and identified just over 4,000 of them that had causal variations associated with outcomes. So that's a lot of genes for which we don't know causal phenotypic outcomes. That's not to say they're not associated in a GWAS or something like that. We took the orthologs of those 19,000 genes over there on the right, and in the 5 most commonly utilized model organisms, mouse, zebrafish, fly, C. elegans, and yeast, and looked at causal variations associated with those genes, and we came up with 16,028 genes. And if we take the union, we now have 84% coverage of the human coding genome. So that's a lot better understanding of the relationships between genotypes and phenotypes that we might infer for what those human genes might be doing in that sort of hand bubble over on the left, where we don't actually know much about those causal variations. All right. So we put this all together in a giant knowledge graph, and I put this slide in largely for, I know most of you are computational if you're interested. All of the data that we put together in the Monarch Initiative is available in an API as well as in a knowledge graph exchange format. There are approximately 818,000 gene to phenotype associations from 50 species now in the knowledge graph. What do we do with it? This is a very detailed slide, but just suffice it to say that we take some of these data and we're increasingly starting to add more and more species to this process, where we basically take a patient in the middle, we have a whole exome or whole genome sequence for that patient, we annotate that patient with phenotypic terms from the human phenotype ontology, and then we combine fairly standard methods over there on the left to remove off-target variants, remove common variants, remove benign variants, remove variants that are inconsistent with the mode of inheritance. This is your standard diagnostic pipeline for rare diseases today. And we add the phenotypic features and the comparisons against those model organisms, as well as protein-protein interactions for guilt by association. And that really helps reduce the overall number of target variants that might be causal for a patient's disease. So this is one of those success stories. This is Jessica. She was 4 when she came into the Genomics England context, and she had a rare condition that caused epilepsy and affected her movement, and all of the standard tests were negative. And so we started out with over 6 million variants. 677,000 of them were rare, 2,826 were predicted to cause a change in protein. And basically using this method and the tool that we've developed to take into account these different data sources, ranked one gene in the top 3 candidates. And it turns out that in this case, this was a de novo deletion in the SLC2A1 gene, which is successfully treated with diet. So this child is growing up. All right, now I have to talk about COVID. So over the past several years, as I mentioned before, we don't have national healthcare systems, so we don't have national healthcare data. So when things like a pandemic happen, it's very challenging to do the kinds of analytics that we need in order to understand, what predisposes somebody to be at risk for severe COVID, or what sorts of conditions or drugs might ameliorate or exacerbate COVID. And in the early days of the pandemic, this was really critical because we really didn't understand this disease very well at all. And even today, there's just a lot of unknown questions about COVID that we can still study using clinical data. So we developed this pipeline, and I should mention at the outset, and I'll get to the team science part at the end, that this is the work of thousands of people. So I'm just a proxy here. And what was really great is that over there on the left, we already had these distributed clinical research networks, the Odyssey network, the ACT network, a commercial vendor, Trinetics, and BCoreNet. And we were able to talk to all the different institutions and these different research networks and work together to develop a harmonization pipeline that would map all these different common data models that their electronic health record data was encoded in, and bring them all together into one primary secure enclave. And I should mention that these are unconsented EHR data from these clinical centers. And so we needed to find a way to scale all of this, the promise of all these mappings. So these are very inconsistent common data models, as I mentioned earlier in the talk about mapping schema and values. And so now this cohort is now the largest HIPAA-limited data set available for public research nationally in its history. And it has over 16 million people in this data set. So it's a very, very large EHR data set. And it has data from now 232 different clinical organizations that were transferred by regulatory authorities in 76 different kind of coordinating units. And it's all driven, there's a dashboard there, so you can go and play around with what kind of data we have in there as sort of summary statistics, all driven by open APIs, and they can also be incorporated into third party. So this is what the pipeline looks like. So every data site has a pipeline for transforming its data according to those schema and value manipulations that I mentioned earlier, as well as going through a large variety of quality assurance and quality data repair methods along the way, with over 50,000 transforms, with every transform fully properly. So now we actually have all the records of what we did to the data, how we said this identifier is back to that one. Like, what do we mean by that? And so this provenance, also allows us to very quickly identify quality issues. To go back, is it one site? Is it one transform? Does the transform apply to all the sites? Does it apply to sites that only look like this? These kinds of issues, and we can refresh the whole thing in less than 20 minutes. So having that transparency there, and in the clinical research world, there's a lot of retraction because the data is not really readily available, and it's fundamentally a challenge, and I think a wonderful opportunity for the DREAM community to have this rich EHR data available from across institutions, so that we're not building machine learning algorithms based on one institution's data, which looks like one institution's data. We really need to be able to make these things translatable to a much broader context. And so this type of provenance allows us to have a much better rigor and transparency around how we develop these methods. So I think I've already mentioned, these are just kind of showing you some examples of some of the different kind of visualization tools that we have for managing that. So you can click on any one of those buckets and get a record of all of the provenance transforms in a big table, and then be able to repair them as needed. So I wanted to talk a little bit about the difference between federated querying and centralized analytics. And I know there's been a couple efforts in the DREAM community to really leverage federated analytics for some of the challenges. And I think that there are synergies between the two. As I mentioned, we could not have built the M3C if it hadn't been for those distributed research networks that already pre-existed. And when we think about federated distributed research networks, the way in which they're used in the clinical setting right now is really that we can ask questions and then we have to trust the individual data partners that have structured and quality assured their data correctly to be able to answer those questions robustly. And some of the machine learning algorithms that have been developed for those distributed networks are really quite sophisticated. Others that we might want to have that we can run on centralized analytics would take decades to actually run with the compute resources that we have now in a distributed setting. So some of the kinds of things that we can do with centralized analytics is not possible in that distributed network. Furthermore, that trust about the sources really having their data modeled and correctly quality assured is a big capital T trust, because fundamentally everybody's doing it in a vacuum with just the specifications that they've been given. And it's not until we actually centralize the data that we can see how well some of those specifications have really worked in terms of data standardization. Furthermore, we can just ask fundamentally different kinds of questions that So I think it's also important to remember that just because the data is harmonized doesn't mean that it's homogeneous. So for example, the different common data models have different expressivity and include different things. And this is somewhat analogous to the example with the race. We need to know the provenance of what that other category, what was done with that. Well, here, for example, in the Odyssey community, we have to have a death date indicated as part of the requirement of the model for the quality assurance text. If that death date is empty, it means that that person is alive. You would be surprised how hard it is to find out in this country who is alive and who is dead. And that was one of our problems in the early part of COVID. We have 5 different sources of death data in order to triangulate, figuring out who's actually alive and who's dead. And part of the reason is what's shown here. So The coronet does not require a death date. So a blank field there does not mean that they're alive or dead. It just means that we don't have the answer, right? And so, these differences really matter when you're analyzing your data. We've seen a lot of examples of deeply incorrect conclusions because it's not well understood how the data is modeled and how it's harmonized, because it's not necessarily homogeneous. So this is an example of just what that looks like for centrally curated and scaled data quality measures. So on the left are a bunch of different ways that individual institutions code for a positive or negative COVID test. And these are just 16 of the sites, and you can kind of see some numbers kind of showing differences across the sites. And so we need to be able to harmonize who's got a positive COVID test. What does that mean? What is the definition of positive COVID test? And we can look at things across sites and across time to look for issues in the data. So for example, the number of COVID positive tests versus the number of negative ones. If that number changes substantially, there should be a good reason for it. That was the pulse that we saw in New York City, or the whole country was undergoing Omicron, versus all of a sudden one site had a whole lot more positive cases and none of the other sites did. So kind of looking at these kinds of things. Average number of rows of data per patient per table. This simple stuff to really see, like looking for where tables might have dropped patients or something like this. Plausible demographic distributions, visits that have negative length. So we have patients that never even started their visits because their timestamps didn't add up. Another example that I think is really exciting and also might be a great subject for future DREAM challenge is algorithmic data repair. So one of the really interesting things is just how disparate and crusty the units are that are expressed for various laboratories and other procedures that have units associated with them. So for example, humans measured in grams do not look the same as humans measured in kilograms, and we actually had quite a few 100-pound babies in our data set. And there's things that we can do about that because basically, if we can develop a series of rules or algorithmic processes that help us prepare those data, so we can guess that babies who weigh 100 pounds probably are not pounds. Let's come up with an algorithmic rule that if it's in a certain range numerically, that means it's probably in grams, kilograms, right? And go ahead and make those transforms again, fully provenance. And so we went basically taking the whole data set at the time. The light green is the canonical units, so those are correct units for this set of laboratory tests that are shown on the left, different kinds of units. And all of that repairing strategies repaired the blue parts on the left. So that's a huge, basically half the data set got repaired in some way or another and was able to rescue all of these files. Again, remembering where your data comes from when you're doing these large-scale DREAM challenges on laboratory data that has units. Well, what about those units? Did somebody fix them for me beforehand? If not, should I be fixing them? What should I assume about those units? Because it's not as simple as just what you might think. Another, and I put this slide in specifically because I thought it would be another great idea for a DREAM challenge. We've done a lot of work on what's called patient privacy preserving data linkage. So a lot of the problems that we have in the clinical side is that the patient's data gets taken apart into all the different data types and sent in different places. We send our genomic data, the genomic data commons. We send our clinical data in an EHR system. Our imaging data lives in Metric. We have viral variant data that's in a viral variant data. All these different pieces of information about a patient really help make it hard to actually evaluate the collective data about a patient. And so this patient PPRL, patient privacy preserving data linkage, allows us to put the patient back together again, but not have the data leave through a secure system. So how do we, again, it's another distributed kind of analytical task because the clinical data cannot leave NTC, for example. We have our 5 different sources of mortality data. We have our insurance CMS data, and these data sets live in different places, but they're all linked. So we know which patient has which data in which location. It's a huge computational challenge. All right, well, what did we do with the COVID data and the N3C? And this is just to give you a taste for some of the things, again, might inspire some challenges. Across the nation, there's an ICD code for diagnosis of long COVID called U09.9, which means post-COVID-19 condition unspecified. And that little graph on the top left shows you in pink the number of counts for patients that have had that U09.9 code applied. And as of today, in our 200 plus clinical sites, roughly half of those sites are now using long COVID code, even though the code has been around for more than a year now. So it takes a long time for these coding systems to come into effect and get used, and different clinicians also apply different practices. So we've got this really heterogeneous landscape of different sites and different clinicians applying this code. There was another code that was used before that that's just sort of any post-viral condition that's shown in blue. And what we were able to do is to basically look to see, well, what kind of people are actually getting, this diagnosis of the UI9.9 code. And you can kind of see just some statistics over there on the right. And I think one of the most interesting things is we did a little bit of clustering and found out that, patients that are less than 21 years old had distinct respiratory and gastrointestinal clusters that were not seen in any of the other groups. So somehow that code is being applied to a specific set of pediatric patients that might be very interesting to further examine for those kinds of mechanisms relating to long COVID in pediatric patients. This is another really exciting outcome. Early on, we had the most Paxlovid data when Paxlovid was first being used to help prevent acute and severe COVID. And the White House came to us and asked us for statistics to look at whether or not patients who had received Paxlovid were rebounding or that we were still seeing the same negative outcomes of patients we might predict would have severe outcomes from acute COVID. And we were able to find out that few patients were hospitalized post-Paxlovid, and those that were already significantly sicker and had a lot of comorbidities beforehand. And so that was really great preliminary data that allowed the White House to decide to invest in more financial resources to purchase more Paxlovid for the nation. Some of you probably have received Paxlovid. It's in part from some of these early investigations that we were able to provide this data to sort of understand the initial impacts in a sort of real world setting across the nation for Paxlovid. We were also able to create a machine learning algorithm that identifies long COVID or past patients before they're diagnosed. So basically took EHR records for those patients that had either one of those U09.9 codes or had been seen in a long COVID specialty clinic, used that as a training set and learned patterns of features of long COVID, such as dyspnea, fatigue, not being vaccinated, having a new albuterol prescription, and these kinds of things. And then use that machine learning computable phenotype to identify patients with long COVID in other contexts where they hadn't been diagnosed with the U09.9 code. And as I mentioned before, we know there's a lot of sites that still haven't implemented the use of that code. So being able to identify them for research studies or for specialty care is actually really important for their care. And our estimates right now, depending on where you set your inclusion exclusion criteria, cover around somewhere between 18 and 21% of people with COVID end up with long COVID. So we also were able to look at vaccination and how preventative vaccination is, and showed with two different types of analyses that there's a statistically significant reduction in long COVID risk associated with pre-COVID vaccination. So one more good reason to get vaccinated. And this, I put this in there because I wanted to show the importance of that data linkage. So this leveraged those vaccine data coming from state health information exchanges. So we really need to put the patient back together again to be able to ask even the simplest questions like, does vaccination prevent long COVID? So this is another, I think we were just talking about this at lunch, another great example of ways in which we can think about using the DREAM challenge as an opportunity to really validate our algorithms in new ways. So in this case, we took that long COVID computable phenotype machine learning classifier for long COVID. We were able to work with the All of Us team and recapitulate that phenotype in the All of Us platform. It was imperfect. They had very few number of U09.9 patients, and we did not retrain the model on their patients. We ran the classifier. And some of the features that were available to us in our data were not available to us in these in the all of us platform. I think it's really interesting context for validating a computable phenotype because we built our computable phenotype based on that 200 plus clinical sites data and making sure it kind of worked in all the different sites. And then we wanted to move that computable phenotype to another multi-site, which has hundreds and hundreds of sites in the All of Us platform, you know, and how are we going to validate that? And how are we going to even just run it in that other setting? And so, you know, I think it was really challenging to think through that, but being able to demonstrate that was really terrific, and they were really great to work with. All right, so a few DREAM challenges that kind of were going. Some of these happened before COVID and before the N3C, and then I'm going to end on a few things that we have going on right now. So this was an EHR DREAM challenge that was led by Tim Berquist at UW and Tom Schaefer at Sage. And this was before we had the M3C. And they used EHR data from one clinical institution. And the question was, given past EHR records, predict the probability that the patient will pass away. And so basically EHR is the patient data, we have the longitudinal data, we have the trained model, and then, you know, a probability outcome. And so, you know, it's just, we had, you know, a decade of data warehouse data with 1.3 million patients that had at least one visit, drug exposures, observations, conditions, measurements in the OMOP data model. So again, that's the model we've been using in the NCC. And so the outcome was just, you know, we had quite a lot of participations in the different rounds with 69 models accepted at the end. And here you can see some of the outcomes from the final submissions. And so it was a really great way to kind of, I think, bring more of the DREAM community to using EHR data for DREAM challenges. Then we did a COVID-19 one, and I'll just keep this one really briefly. This is right when COVID was starting again before the N3C was built. Among patients who tested positive, predictive results of the initial test, positive or negative, using data available at the time that the test was performed. Right, so that's really clinically relevant. Looking at this patient in front of me, what's the prediction about whether or not they're going to be COVID positive or negative? And then for those that are positive and were tested in an outpatient visit, which patients were admitted to the hospital within 21 days of their test? And I think it's important that, in particular, that first question about, you know, who's going to test positive or negative, because it could be based on geographic information, demographic information, and the clinical measures. So we're not just saying that, you know, a given person is going to test positive because, you know, they happen to have diabetes. That wouldn't make much sense. But because they had diabetes and because they live in a certain place and there is other demographics. This is really getting at, you know, trying to understand health disparities and differences in the waves of COVID as it moved across the country. And this was just some of the outcomes over time, which is really nice improvement. Okay, so then we had the N3C was instantiated. And so next, BARDA had wanted to do a challenge with us. So this was a pediatric challenge to look for deployable models to predict hospitalization in positive pediatric patients. And then second, to predict severity, such as the need for cardiovascular support, invasive mechanical ventilation, or ECMO in hospitalized children. And so that challenge is concluded, and the winners have been announced on the BARDA website. And we had 200 participants with 88 teams, and 55 models were submitted for both tests. So it was really exciting to see the N3C data used in a challenge. Okay, so I'd love to come up with new challenges that we might do with the DREAM community using the N3C. So just harking back to Paul's earlier talk about the Bridge to AI program, our group leads two of the cores, the teaming core and the standards core. And just hopefully I've really inspired you about all that data preparation parts over there on the left, and what it means for, you know, our machine learning models and algorithmic work in the context of these challenges, or more generally about how do we, you know, generalize them across systems and sites, and how do we include different types of data available to us in different structures And so, fundamentally, the way in which we prepare the data, make it available with the provenance, and better use the provenance in how we're defining our machine learning methods, can really sort of help drive the way in which this whole Bridge to AI program is really going to function. And so our emphasis is really on that sort of upstream part of really helping teams put their data together in meaningful ways that where we know the provenance and can use more of that sort of data preparation details in our models, so that those models are more robust with respect to translation across systems and places. I wanted to talk really briefly about attribution and I spent a lot of time talking about provenance. But one of the things that we get with the provenance is we also have the ability to do what I call transitive attribution. So essentially, here we have over there on the left, we have an agent that has a specific contribution to a specific artifact. So my example here is Tiffany Callahan. She's been a terrific graduate student who just graduated recently at the University of Colorado. And she curated this amazing data set that mapped a whole bunch of ontologies to the OMOP standard. And that data set's available at a DOI on Zenodo. And it's also available in the N3C enclave. And so over there on the right is in the enclave shows a provenance graph between results, code, and source data for a full end-to-end provenance chain for someone's analysis. And you think about every one of those boxes, the red boxes and the yellow boxes, has different people that are attached to them. And we can track and audit every single person who touched every single one of those files. So when we run an analysis and there's a report out the other end that goes into a manuscript, we know everyone who contributed anything to the bucket brigade. That was all of the data preparation, all the modeling, all the harmonization, as well as all the artifacts like Tiffany's artifacts. And so we've really pushed on this idea of transitive attribution and making sure that the folks who help all along the way get an opportunity to participate as authors on these manuscripts, and that these artifacts themselves, if and when they can be shared in GitHub or Zenodo and other public places, that their ORCID IDs are associated with those. And in fact, it's a requirement to have an ORCID identifier to actually get into the system. And this is just this shared knowledge library. So people can share their code sets and their artifacts and their knowledge mapping files like Tiffany's file in this sort of knowledge store, which allows the reuse of these artifacts. And so a lot of the sort of tables that we've generated, and artifacts that we've generated, and methods that we've trained are now available in this store for other groups to pick up and use in their work. And so we're really expediting the science together by reusing each other's work. But that's because we've changed the incentive. Now there's an incentive to share your artifacts once you've gotten into a robust state in this kind of context, because if somebody uses them, you're going to be an author on their paper. And so it really flips clinical informatics on its head with respect to the incentive structure to stop hoarding data and artifacts and start sharing, because the impact is so much greater and the science goes so much faster and it's so much more robust because more eyeballs are looking at things all along the way. And so, just to kind of speak a little bit about that, and I think, in the DREAM community, it's often, molecular computational challenges, but in clinical informatics, we don't really collaborate that much. It's a very competitive data hoarding type of community. And so the N3C and the as they say, never let the pandemic go to waste. The unprecedented collaboration in clinical informatics was due to the pandemic, because people really wanted to save lives, and they thought, hey, if we share data, we share technology, we work together, we'll actually find the key things. And we did. I'm not really speaking too much about the impact today, but we changed care for cancer patients, we changed care for transplant patients, HIV patients by using these data collectively in this way. There are over 4,000 participants in the N3C. The first paper we submitted to, and I'll show you it at the end, to a clinical informatics journal, took them over a year to index all the authors in Medline, because they've never had a paper with 200 authors on it before. And so we've changed the journal policies about authorship. There are 32 multidisciplinary domain teams. So, we basically try to pair clinician experts, machine learning experts, epidemiology experts, statisticians, bioinformaticists, all together in these specific domain teams that might focus on kidney disease or rural health or social determinants of health. And these domain teams really are working together to kind of bridge the translational divide because most of the clinicians who have the really important clinical questions are not themselves like, machine learning experts. And so bringing those people together in these domain teams also allows that sharing and attribution of the different artifacts. And the clinicians are just having a ball. So like, ask this question, no, ask this question, no, ask this question. And, the folks who are doing the coding can really like get after the data in kind of real time. And it's been a really wonderful, collaborative, and enjoyable experience. We also have an incredible training portfolio that's been accessed now over 5,000 times. There's like 763 different resources in the Enclave for training people. We have office hours every week. We even have high school students who have done projects in the Enclave by just playing one of those teams and going through some of the tutorials and whatnot. We also created some best practices for various kinds of things like machine learning and NLP. If you go to that link at the bottom, again, it's the same dashboard, but there's an admin. You can play around in that little social network graph are projects and institutions showing the interoperability between artifacts, people, and resources in the Enclave. So you can start to do science about how this collaboration is actually working. All right, so just to kind of start to wind down here, hopefully I've implored you to think about how all the dots are connected in your data sources, both as part of your own work as well as when you receive a data set that might have had on it beforehand. And I've got some silly acronyms for you. One is codes, which is tools, ontologies, algorithms, data, and standards. And if we take that set of things and we matrix that with the sort of standards, fair, findable, accessible, interoperable, reusable, but I also add on traceable, licensed, and connected, because those are really fundamentally the things that make data truly reusable. This kind of matrix really kind of gets after all the things that we can all do to help improve connecting all the dots, right? So, basically making sure that the licensing on everything we do is made for redistribution, or the lack of modularized, Dockerized components means that we can actually move our tools from one place to another. There is a new NIH-led long COVID challenge. So I just wanted to point this out. This is not a DREAM challenge, but using the N3C to see if you can improve on our machine learning computable phenotypes if you're interested in that. And so I anticipate there'll be a lot of people who will be able to do that. This was just a first, endeavor for us, and there's lots of different ways that we could think about developing new models for actually having evidence-based definitions of long COVID. And then these are sort of like little mini challenges. So the National Center for Advancing Translational Science, who is our sponsor at NIH, has a new contract mechanism that allows kind of quick turnaround analytics, and you can get a contract for up to, I think, $50,000 to do some analyses for things like the tax use case that I mentioned earlier, where they need a 2 to 4 week turnaround. And it's team science, so you would come in one of those domain teams and work with the other folks in the Enclave to kind of help do that analysis. And it's a way of getting new kinds of expertise and new interests from the community, as well as having more rapid turnaround on some important questions that we don't always have the bandwidth to answer every single one. We've gotten queries from senators, from the White House, from HHS, and other places. So there's lots and lots of opportunities for you all to participate in kinds of challenges as well. And then I just want to close up with some thank yous, and I would be remiss if I didn't thank a very large number of people. So for all the work that I presented at the beginning about the disease reconciliation and disease diagnostics, the very large community, the Monarch Initiative program, which is co-led by myself, Chris Mungle, and Peter Robinson. And I want to thank all the data providers, because we're the quintessential research data sites. But none of our work would exist if it wasn't for everybody else's data. So with great gratitude to them, and also for NHGRI and the Office of Director for believing us and continuing to fund us. And then this is that manuscript from the N3C that was the first manuscript. And there's some really interesting attribution policies about what constitutes consortial author versus masthead author versus acknowledgement. But this was the paper that took over a year for the journal to index everybody in Medline, so they had to do that before. And so with that, maybe hopefully have time for 1 or 2 questions. Thanks.
So my name is Yosuke Tanigawa, a postdoc at MIT. So my question is trying to combine the success in the XMiser space as well as the electronic clinical record, try to represent those genomic information in the context of each EHR. And I wonder what's going to be your vision in terms of how do we represent those kind of XMiser types of discovery as a part of the patient's medical record.
So we've been working on that, and we'd love your help if you want to join us. As part of an HL7 project called the Vulcan Accelerator, where we've been working to, we have a standard called Keynote packets that was originally developed in the Global Alliance for Genomics and Health, it's now an ISO standard. And that standard allows the phenotypic representation of a patient that would be the intake for XMiser. And the HL7 project aims to represent that as an HL7 FHIR message coming out of the EHR. And then together with the clinical genomics group in HL7, they've been working very hard on putting the outcomes of XMiser and other variant interpretations back into the EHR. So one goes one way and one goes out and one goes in. And so that's, I think, the way in which we're going to actually standardize that kind of content in the context of the EHR. I think more exciting and the clinical but we're getting there. More importantly, I think, is how do we actually analyze the clinical data at scale together with the genomic data? We have lots and lots of genomic data, we have lots and lots of clinical data, but there are a number of patients that come back together and have a whole data set. So with these new PDRL, patient-derived reproducing data technologies, we can actually start to do that. So what we really need to do is figure out as a community, how do we get all our genomic data sets that are going to places like genomic data economy or wherever, and actually create those record linkages so that we can use multimodal kinds of analytics and actually refine. So I'm not just using hand-curated data about individual disease entities that are both standard for our XMiser tool and organism data, but actually real clinical data that can combine those XMiser types of approaches with more standard machine learning and both clinical data and genomic data. And that has not yet happened anywhere at scale, although it's close to this partnership, but they don't have clinical data like we have. So I think that's where the real science is going to be used.
Yeah, really exciting. And I think not only looking at the Mendelian types of disease, but looking at how to represent the contribution of non-coding genetic variant, either through polygenic score or other types of mechanism, and try to how to jointly analyze a potentially whole genome sequencing of thousands of individuals in the context of EHR. How do we guide it? Loop it back to the clinical practice is the really exciting area. So thank you very much for the overview.
Yeah, and I'd love to talk to you some more about that.
Thank you.